Okay, so hello everyone. So today we're gonna talk about the spill coffee effect. So what is it? I think you have all experienced this. It's when you're just walking up with your coffee and you try to keep your coffee in the cup, but sometimes when you're walking, well, the coffee overflows and then you spill your coffee, unfortunately. So we're gonna study this effect, how it appears, based on this paper of those researchers, and also how to prevent this effect in the industry. So first, we're gonna establish a general model for our study. Then we're gonna show the experimental results from it, and then we're gonna discuss on some industrial applications.
So in the paper we read, what they have done is following the motion of the cup. So they track the motion along the x-axis and the y-axis. So here you have two plots. The first one is the plot of the velocity of the cup along the x-axis. What we can notice is that there is two regions. A first one where there is an acceleration, and another one where the velocity is constant. And the second plot show that during the motion, the cup of coffee oscillates along the y-axis during the acceleration region and also the constant velocity one. The combination of those two parameters lead to an anti-symmetric sloshing response, which will let your coffee flow out of your cup. So yeah, you start the human object start from rest and start to walk. So to describe the parameter of the model, we assume that the human subject is walking in a straight line path along the x-axis, and that the cup of coffee stays in the plane of motion. To talk about more of the modelization of the cup, we assume that the cup is a cylinder, and we can define the coffee spill angle, which will be the maximum angle that your coffee can have in the cup without spilling, which is represented here. And thanks to this coffee spill angle, we can also define the coffee spill acceleration, which is related to this angle. To talk about now the assumption that we made on this to study this model, we make assumptions on the coffee property. We assume that they are close to the water, so the bio number is pretty high, so we can neglect the surface tension effect. And the Reynolds number 2 is high, so we can neglect the effect of viscosity. As I said, we assume the cup is a cylinder, and the coffee spill angle alpha is a parameter that can measure that can be related to the level of coffee. We assume this angle is between 8 and they assume in the study this angle is between 8 and 16 degrees. And to finish, they assume that the excitation that the cup receives is the same as the frequency of human walking step, which is between 1 and 2.5 Hertz. So thanks to all this, in the study they calculated the equation of motion, and they solved the eigenvalue problem, and which leads to this formula of the natural frequency that they found. Thanks to the assumption we've made previously, they simplify it with this formula. So because the problem is nonlinear and cylinder, we have some Bessel functions that appears, and they solve it using this value, which give us this natural frequency of 3.6 Hertz, which is close to the natural frequency of the cup, close enough to have the effect of an amplified response, even if we are not in the natural frequency.
So, as Gaëtan said, the basic theoretical explanation of the coffee spill is the resonance of the fluid. However, it doesn't explain completely the phenomenon. And as we can plot the motion of the mug, we can see that there is some noise on the motion profile. And this makes a good transition to the second part, which is focused on experimental results to explain this noise. So as we can see noise on the fluid's motion profile, the paper then needs to study the influence of other parameters on the coffee spill effect. And so they make an experimental study of the time before spilling coffee while walking, which is basically the number of steps that one can do before spilling its coffee. So how long does it take to spill? The involved parameters are the maximum acceleration, which is directly linked to the walking speed, and the coffee spill acceleration. And then the paper studies the ratio between them. And when the maximum acceleration matches the coffee spill acceleration, we can say that there is an instant spill. So whenever the ratio is over 1. The other parameter, as I said before, is the number of steps before the coffee is spilled. So it's N. Now if we look at the basic correlation between this ratio and the number of steps before spilling, we can naturally see that the number of steps required before spilling the coffee decreases as the ratio gets closer to 1. And then we can also make the conclusion that the number of steps before spilling decreases as the walking speed increases. So then the study wanted to determine some other external parameters to explain the noise. And we can firstly talk about alpha, which is the coffee level angle. And this also represents the level of coffee in the cup. So we can see on the plot that the number of steps before spilling coffee decreases as alpha decreases, which means quite naturally that it takes fewer steps to spill when the coffee level is high. And the other parameter is to what extent the person is focused on not spilling the coffee. And we can see that when someone is focused on the coffee cup while walking, it takes more steps before spilling the coffee.
Yes. So just to sum up, there are 3 main factors that makes your coffee spill. So first, the coffee spill acceleration. Then the resonance effect. So if your cup excitation frequency, so like your footstep frequency, matches with your natural and symmetric coffee mode. And a last factor on which the paper insists, which is the human factor. So if you are focused on unfocused when you are working with your cup of coffee, then your coffee can spill. And of course, the environment that can disturb you. So now let's talk about 2 industrial applications on how to prevent this effect of the spilling fluid. So first, preventing the tank sloshing for trucks. So let's say you have a truck that carries on a fluid like oil. Then this fluid, when the truck is moving on, has a back and forth movement as in the cup of coffee. And well, when the truck stops, this fluid has a force that can extend the length of braking. So if we play the video, you can see the fluid inside the tank of the truck that has this back and forth motion. And so to prevent it and avoid some car accidents, you can put inside the truck bulkheads that split the tank in many parts that reduce this motion and then reduce the braking distance. So the simulation said that for a speed of 19 kilometers per hour, it reduces by 10 meters the braking distance. And so this is like the same application for a rocket propellant tank. So the gas inside the tank of rocket can affect the trajectory of the rocket. So in order to avoid it, we put some plates, as you can see, inside the tank at each level inside. And so they are called anti-slosh baffles, and they damp the energy of the fluid inside the tank at each level in order to avoid this back and forth motion. All right, thank you for listening, and if you have some question, feel free.
Audience questions?
This is a weird question, but I drink a lot of coffee. So when I'm walking with my coffee cup, if you swirl the coffee, it doesn't want to leave as fast. I just wondered if your paper talked about that at all.
They talk a bit about.
Sorry, yeah.
In the paper, they didn't mention the fact that if you turn, you reduce the thing. But what they said, because we simplified, because they were talking about a lot of things, the mode shape of vibration of the coffee, we presented only one, which is the back and forth, but in reality you have 4, and the back and forth is the main one with the movement, and you have also the second one, which is the second important, is the one, as you said, of rotation. So I think maybe when you rotate your coffee, you cancel this shape mode, and which will enable to reduce the global movement of the coffee in the cup.
Thank you.
You're welcome.
Well,
Yes.
well, why does it prevent spilling?
Maybe if you excite the mode shape, but in the opposite way of the natural way it will express when you walk, you will suppress it.
I think it's an angular momentum, maybe, because it has some angular momentum and takes some torque extra. Your calculations, there's no angular momentum. It's basically the gravitational force. But basically, if you have to change the direction of that torque vector, maybe you just don't have enough. You don't have enough forcing. That's what I'm guessing.
Yeah, I was asking, like, what I understood is that there exists a maximum velocity, and if you go beyond that velocity, there will be instant spill.
It's approximately this. It's not about velocity, but maybe also.
Yeah, it's because the people online can't hear through this.
So the paper focuses on the acceleration, and yes, when you go beyond this acceleration, they consider that the spilling is very fast and it's almost instant spill. So
my question is, like, if the acceleration is less, even then, is there a criteria if you exceed, like, for example, 100 steps or 200 steps, even then the coffee will spill, irrespective of your acceleration?
I'm not sure.
Let me rephrase it. I'm asking that if I go beyond certain acceleration, then it will be instant spill. But my acceleration is, let's say, not close to the critical acceleration. It is less than the acceleration. And you have shown the number of steps plot, right? That for certain acceleration, you require so many steps for spilling. So my question is, if your acceleration is less than x double dot alpha, even then, like, there exists a number of steps beyond which the coffee will spill?
So you're talking about the left bar.
Yes, yes.
They actually don't really mention that in the paper, but I guess if your acceleration is close to 0, you just don't move the cup and you're not walking. So I guess there is no spilling and you cannot spill it.
Thanks.
Can you talk a little bit? You had go back to the bond number, Reynolds number equation. Just tell people briefly how you got to the velocity scale.
So
the velocity scale and Reynolds number. Like, tell people.
Velocity scale is this term.
Yeah. So how'd you get it?
Because it's related to this acceleration, I suppose. Oh, sorry. I think the velocity scale is they build it this way in the study because they relate it to this acceleration here, which depends on the angle and the gravity. So I think they are related this way. This is how I understand it.
Yeah, this whole thing is like a pendulum of coffee. Pendulum has like kinetic energy and gravitational energy. And basically, when it's on the upslosh, it's basically not moving, and then it has moving. And basically, that's that's like the length scale of the pendulum, which I guess is your radius of your cup, and the time scale of the sloshing, which is square root of G over R. That's how I get that. How do they figure out coffee is between 8 and 16 degrees? Is that based on how people fill the cup? Because no one wants to walk around with like an empty cup of coffee.
The thing is that this angle, maybe I can answer if you want. This angle is related to the level of coffee that you have aged. So what they say in the study is that they say when someone is filling his cup of coffee, it will naturally fill between those two angles, which correspond to a certain level.
Okay, so that's like 3/4 full.
Yeah, they could have converted this into level of coffee.
One more slide. So they're like, I was actually curious. You meant, how do they get this dispersion relation? Like you said, some kind of method.
As far as I understand, it was. So in the yeah, no, because this was kind of a shadow part of the study. This relation is actually because the equation of motion they establish, it's kind of tough to understand, and what they conclude is a nonlinear equation of motion that they derive from Euler-Lagrange equations, and by solving the problem based on other papers that they mentioned, they said, okay, other person calculated that for this kind of problem, natural frequency would be this horrible formula.
So they didn't actually solve Navier-Stokes, the pendulum.
In the paper, no, but they refer to other paper that did.
Basically, if we did, it look something like this.
Okay. You notice that citation, 1964, NASA? Oh. That's because they noticed this, that they move the rocket, the NASA space shuttle with the rocket, they move it, and then it's still sloshing. And so they had to basically, how do we actually stop this sloshing? And that's maybe after that. You probably have to follow. Your paper is after that. Your paper is not 1964.
No, the paper is more recent.
Huh. Any other questions? Okay, good job.
Thank you.
I've just got some Halloween candy. Feel free to take some. All right. I think your cup of water, your coffee demonstrations over here. Who's who's next journal club? I think we're not going to do Wednesday because there's quiz Wednesday. We'll be doing it. There's 3 classes after Thanksgiving. 3 classes left for this whole course after Thanksgiving. Well, I think we'll use those 3 classes for the course project presentation. How many people signed up for presentations?
Oh,
I mean, we all have to do presentations, right?
Yeah, but I think there's groups. Does anyone remember the online form? How many people are signed up?
Last time I checked, there was 2.
There's 20 people in the in-person class. If we have an average of groups of 2 to 3, that's 10 groups. 10 groups in 3 classes would be fine. 10 groups in 2 classes would be a little tight. So I think I think we can fit them in.
Are we showing up for the day class presentations, or there's no class final, we just don't show up on that finals weekend?
I think you all prefer not to show up. Just my guess. So I think we just do them all at the end of class. The final period is 3 hours long, here's the issue. If we have one person present before Thanksgiving, they'll be like, oh, everyone else got 5 more days. And also if we do the final presentation, like on the final class, we're like, oh, I got 5 more days. So I think we can just do it in 3 classes at the end of the class after Thanksgiving. So people will have within 1 week to work on it. So that sign up sheet, please sign up numerically in order. And I'm going to put the 3 dates, and so you can select which date. But you can't all select the last date. So we do need some brave people. And keep in mind, we'll grade a little nicer for the earlier dates because we can't all present at the last minute. And you've had a little bit more or less time than everyone else. All right, so we have another presentation Monday next week. Cowan, and then Daniel. Monday? Are you guys together or not together? Okay. Okay, so we'll have 2 presentations. What are you going to talk about? Do you know yet?
I'm thinking about the fish scale.
Fish scales? Okay. Daniel, what are you going to talk about?
I have a topic. I have to look it up again, but it's instability.
Okay. And Cedric's going to present too. But you guys figure out if you want to do. One of you guys had to present on Wednesday. I guess we could have 2 on one day. All right. Let's see. All right. So remember, there's quiz on Wednesday this week. Online people, I think there's actually someone whose partner is having baby on Tuesday, so they probably get excused. They're gonna just take it sometime before the baby goes to college. That'll be good. Remember, there's basically some on because there were some folks that did not do well on quiz 1. So there's going to be some part that's the Einstein, the index notation review. Make sure you can do those the first part of the quiz from last time. I've given the solutions online. Quiz 1 solutions online. And make sure you actually understand what you're doing, because this will be kind of I would be happy if people actually figure out their errors after seeing quiz 1, after seeing the solutions and doing the quiz 2. If you still get those same ones wrong, it will make me sad, because this is it'll be near the end of the course. And then another one, I think we do startup flow in Cartesian. So you've done two problems with that. One problem was basically in class we had basically u at t greater than 0, and the other one for the homework was tau given for t greater than 0, and you're supposed to figure out what the flow looks like for all the time. So make sure you know the processes for that. Remember, this is a not integration, separation of variables problem, and then this is an eigenvalue solution. Because when you separate by variables, you're going to have basically t of t and we'll call y some function of the height between the plates, z of z. Remember, we'll call it. I forgot what we called it before. I don't want to call it r. L of y. So this is x. So we have a distance between L of y. You have these two. This thing is equal to your velocity field, u of t comma y, and we had the governing equation. So you're basically using this and figuring out what basically the eigenvalues, so the time it eventually gets to your steady state solution. Startup is basically, imagine we had some values that are increasing as we got further and further away from the plate. So just review that, and you should be, I would say you should be pretty good. I will not be giving you exactly these two cases, but I think that's the best you can do to prepare. But make sure you know how to apply the boundary conditions and how to change it into the OD problem. Okay. And we'll have office hours before the office hours today, 7:30 before the quiz. And I have in-person office hours today too, but there's also the undergrads have a quiz on Wednesday, so it might be a little crowded. But I'll make sure to give you priority if you have a fast one. Any questions on, so I said it's Cartesian, so you don't have to study the radial coordinates. I think Cartesian gives you a pretty good idea of what methods you use. Any questions and I'll just give you the whole class, but I don't think you'll use the whole class. But I didn't think you needed it last time either, so that's what I know. But any questions about what you're going to have to do on Wednesday? And that will probably be the last quiz. That will be probably the last quiz of the semester because we're running out of time. All right. So remember the homework we could do next Friday. Not this Friday. Today I pretty much can teach you how to do every problem, and then we'll have Monday. And we'll have a little bit of time today to talk about how we do the problems. In fact, one of the course project people are going to do. Are you guys going to do like the problem, right? But you're not. You're not. Yeah. Did it work? You're building it, right? Okay. Maybe at some point next week you could give like a little update. So I don't think you'll be ready to present it for sure, but I think the fact that you're actually building it will help people understand. So you could like bring a little demo like Don did. That would be great. All right. So there's one problem that talks about complex potentials. So let's talk about that now. So last time, did I talk about potentials? I don't think I got a chance to talk about potentials. We spent the whole time. Yeah, we derived this added mass, which took a long time. All right. Okay. So let's first talk about, before we talk about complex potentials, let's talk about the stream function. And we call that psi. Remember, this is psi. That's how you pronounce it. So if flow is incompressible, we use these stream function potential techniques to solve this conservation of mass equation. Okay, it's incompressible. Density is a constant, so we have this conservation of mass we use for Navier-Stokes. Historically, stream function and potentials came in the 1800s before they invented Navier-Stokes equations. They had all these ideas, but that's also why it led to some paradoxes. Like I think in the homework you have to show that you have zero drag on cylinders. Basically, unless you have viscosity, you can't have drag, which is very, very non-intuitive because pressure drag is density times velocity squared. It doesn't actually have viscosity in it, but the short answer is that when you've got a viscosity, you have boundary layers, and you have wake shedding. And it's the wake shedding due to the action of viscosity that creates a difference in pressure. And only by having the viscosity can you actually get that asymmetry that gives you the drag. But from far away, it doesn't seem like you need viscosity, but you do. But it took them like 50 years to figure that out. So we're going to do, but this is still very useful to do complex potentials when you're at super high Reynolds numbers, like airplanes. All this lifting line theory, everyone in aerodynamics, they do a lot of basically figure out lift of airplanes without any viscosity. So if basically U has no divergence, historically you can write U as the curl of a stream function, where psi is the stream function. I'm going to talk about, well, potential and stream function have very similar information. And this homework, we're going to introduce what's called the complex potential that has both of them. All right. All right. Let's call this the stream function vector. Sorry. Yeah. We need to have it to be a vector. Wait, curl of a del cross. Yeah, you need to be a vector. All right. So, note psi is made unique by specifying zero. Okay, so there's arbitrary. So the information in stream functions is in the derivatives of it. So there's some arbitrary constants. So you can basically make it unique by also specifying that it's divergence free. And this corresponds to basically choosing the gauge of a wire in an E and M. Wire gauge in magnetism. The fluid vorticity is also related to the stream function. So remember, the vorticity is del cross U. And if we substitute this, we have del cross psi vector. And with your identities from homework 1, you can write this as del of del dot psi minus del squared psi. Okay. And because we're requiring that psi has no divergence, this is 0. And so this becomes negative del squared psi. Okay. This is the stream function vorticity equation. All right. Yeah. Okay. So you're probably all right. So you probably haven't seen this formulation because in undergrad you did not do 3D flow. But the formulation for streamlines is actually three-dimensional. So, physically, lines of constant psi magnitude correspond to the streamlines of the flow. If you're a 2D flow, then psi, instead of a vector, psi is always pointed always pointed in one direction. So then it's just a function of x and y. But physically, like in 3D, you can imagine if you got basically this psi, if you have 2D, for example, you have psi equals to psi 1, psi is equal to psi 2. You can show that basically the flow rate q is equal. Oh, that's terrible. Flow rate q can be found just by subtracting the two stream function values, psi 2 minus psi 1. And basically, when you got flow, basically, because the stream, remember the definition of a streamline, this means that it's basically parallel to the velocity field. It's always everywhere parallel. This makes the most sense in steady state coordinates, But people do streamlines when it's not steady state, and you have streamlines that actually can cross and not steady state. But in general, if there's no stagnation points around you, basically the flow between streamlines stays between streamlines. And you can also imagine this to be called a stream. They call this a stream tube. You can imagine a stream tube in 3D as like a cylinder in 3D, and in 2D it's like a riverbed. But basically, what stays in the streamline is like they say what goes on in Vegas stays in Vegas. I don't know why they say that. Bad things happen in Vegas. But what goes between the streamlines stays between the streamlines. All right. Okay, so that's the last we're going to talk about 3D flows. The homework's actually on 2D flows. But just keep in mind that this formulation, there's a lot of machinery out there for your next fluid mechanics class that involves 3D flows. So for 2D flow, we're going to set the psi vector to be psi of x comma y point in the z hat direction. Okay, so the information is just going to be in 2D. So physically, that corresponds to basically we have the plane, and let's say you've got this line here, psi is equal to a constant here. All right. In 2D flow, our velocity field, this is not great notation, but everyone does it. So we're just going to do what everyone does. That we're going to say the velocity vector is called u, and the x-coordinate is called u as well, and but the y-coordinate is called v. Okay, and I'll show you that for u to be the curl of for basically psi dot del dot psi to be 0, this is going to equal to d psi dx negative d psi. D psi dx, sorry, negative d psi dx. And some of you, this might be a review if you've thought about this before. This is for del dot u is equal to 0. Okay. All right. And you can imagine why that is. If you take the divergence of, I mean, we can just do the divergence of del dot u. You can imagine the first component, we got d squared d psi dx dy, and then minus the second one d dy, d squared d psi dy dx. Because the differentiation is commutative, this is going to be 0. So you can see that that's a pretty good definition. That shows that your U is going to satisfy conservation of mass. We just said without proof that the streamlines correspond, that lines of constant psi correspond to the streamlines. We can see why that's the case now.
Equal to minus d phi on dx, please.
Oh. This is what you require for you to get conservation, to get this basically conservation of mass. This is by definition of the streamline.
You just assume that?
So the story is that if basically if you have del dot u 0, then you can write u as the curl of some psi. And the curl of, basically, the curl of this is equal to this. Okay, so if I were to do curl in 2D, you take a derivative of that and then this one. Yeah. So this is, you could also write this as del cross psi z hat. Okay, and that's where this comes from. That's the definition. That's basically if you have something that's divergence free, you can write it as it has both a potential and it also has, I don't know what we call it has a stream function. That's basically what we have. Okay. So the streamlines are defined by the fact that U and basically the paths of the fluid flow are perpendicular. So there's a couple ways you can do this. Let's look at psi, and look at how much psi changes as we go between x and y. So psi, you can write that as d psi dx times dx plus d psi dy times dy, right? And by the definitions of psi with respect to u and v, we have this equals to d psi dx is negative v dx, and d psi dy is u dy. And basically, if you need d psi is equal to 0 on the streamlines, if that's equal to 0, then you have basically u over v is equal to dx over dy. So physically, that corresponds to a line where the slope of the line is given by the ratio of the horizontal and vertical velocities. Okay. So that's why basically the streamlines are parallel to the velocity fields. Okay. So if I were to draw that here, we'd have basically that psi equals a constant. This is like dx, and this is dy. Okay. Any questions on, do people understand why this is equation that's streamline? Because you basically you're imagining you're drawing a line, and the slope of the line is dy over dx, and that's also equal to the vertical extent of the fluid velocity and the horizontal extent of the fluid velocity. This is basically 1 over the slope. Okay. All right. Now let's talk about complex potentials, which is basically it's just a way that people have put the information of both potentials and streamlines into one equation. But also gets into, there's some parallels between complex analysis and fluid mechanics. The complex potential is this. Okay. This is called the complex potential. Why do they call it that? Because it's got both real and complex parts. The real part of the complex potential is just your regular potential, which you learned from undergraduate. And the imaginary part is given by the stream function. So in 2D irrotational flow, inviscid flow. So let's remember what all this stuff means. 2D means you have u is equal to u comma v. Irrotational means that you have no curl. And inviscid means that there's no viscosity. So they're all independent things. 2D flow, if you want to measure something in the plane. Irrotational is if you're considering irrotational flows that don't have any curl anywhere. So not just, I mean, there's some irrotational flows that are, for example, like the irrotational vortex, that there's a singularity that this is not true, but otherwise this is true everywhere. And there's all the flows that we're going to consider, I'm going to show you they are all irrotational. And it gets you pretty far. And the last one is that the viscosity is 0. And you require that so that there's no additional flows as a function of time. Because if you basically have viscosity be 0, the theorem we proved a couple lectures ago said that you're not going to get any more extra rotation. So if all these things are the case, you can write this. U as the gradient of some potential, and U is also the curl of some stream function. 2D stream function means that all the vectors are in Z. So if U is equal to UV, then we have, so basically, given this really, really shorthand definition of U in terms of phi and psi, you can write this. U is equal to d phi dx, which is equal to d psi dy, and V is equal to d phi dy, equal to negative d psi dx. Those are just definition of the curl and the potential. All right. So the mathematicians recognize that, hey, because the velocity field's related to the potential and the stream function, this is actually makes that fluid mechanics is a subset of complex analysis where phi and psi satisfy what's called the Cauchy-Riemann equations, which has nothing to do with fluid mechanics. They use that a lot in other fields. That's not Riemann equations. The Cauchy-Riemann equation says the requirement of differentiability of a complex function. All right, so the Cauchy-Riemann equations tells us that basically if you have your variable z is x plus iy, then the complex velocity associated with that w function is dw dz is equal to u minus iv. In other words, this is equal to u magnitude. So this is a u vector magnitude, e to the negative I alpha, where alpha is the flow direction. All right. I want to give a couple, so let's review what I just said before I give you some kind of like physical ideas about phi and psi. So what did we just say? Okay, we said that I think everyone is probably people familiar. We have this information of the velocity field in both psi and phi, the potential, and psi. And we can put those two pieces of information in this new complex variable where the real part's phi and the imaginary part's psi. Okay. Because U has the following definitions, Cauchy-Riemann tells us, hey, well, the velocity is just, has a horizontal velocity and a vertical velocity, is actually equal to the derivative of w, okay, respect to z, where z is equal to this. And with this notation, that means this complex velocity has a following direction, where alpha is the direction of the flow. We're going to practice with this with a couple different kind of flows. But before we get into that, let's talk a little bit about what physically this kind of means. So note, remember, we're solving conservation of mass. In this case, for 2D irrotational flow, we have this is equal to this, that's equal to 0, and that's because del dot u is equal to 0, and this is because the vorticity equals 0. So when you draw these things, they're kind of going to look like solutions to the Laplace equation. So the plot for 2D irrotational flow. The fact that it conserves mass means that the Laplacian of phi is 0. The fact that it is irrotational means the Laplacian of psi is 0. All right, 2. When you draw streamlines, keep in mind that they're basically perpendicular to lines of constant potential. So for example, this is phi x, and this is psi x plus phi y, psi y. And if we substitute with our definitions, this is u times negative v plus v times u. And that's 0. So physically, what does this mean? That means lines of constant phi are perpendicular to the streamlines. So lines of constant phi, that's a kind of a mouthful. People call them equipotential lines. And that means phi is equal to constant, is perpendicular to streamlines. Psi is equal to constant. Okay. These are supposed to be psi x, phi x. All right. Last thing is basically when a lot of times you're doing these flows, you're trying to calculate the resultant flow around a body. And the best we can have is what's called non-penetrability. Because on bodies, for example, if you do flow past a cylinder or flow past a spinning cylinder, which you'll do in the homework, you're not going to get no slip. So you don't have no slip anymore because you don't have no slip unless you have viscosity. So the non-penetrability boundary condition means that, remember, d phi dn is going to be the velocity into your body, and that's equal to d psi ds, okay, on boundaries. So physically, what that looks like, if you got this solid body, my n hat vector is going to be outward normal, and my s hat vector is going to be parallel to the body. Okay. So basically, when we want to try to model rigid surfaces, we're going to represent them as streamlines. All right. So let me give you a couple different irrotational flows that we actually know the complex potentials for. All right. So what people have done in the past, they came up with these basic complex potentials by solving the Laplacian subject to the boundary conditions. And then they compute the velocities. Because in the end, you probably want to know the velocity fields. Because if you want to know forces on bodies, you have to calculate the velocities in order to use Bernoulli's equation. So let me give you a couple kind of easy to remember complex potentials. And this is definitely not exhaustive. There's definitely more, but they're kind of algebraically a little harder to write. So uniform flow. Let's say we have this is x and y. and we got some flow in basically an arbitrary direction like this. We'll call that. Let's say he's got a horizontal component u naught and a vertical component v naught. Okay. The complex potential for uniform flow is u naught minus I v naught times z. All right, so remember, z has information about our position. Z is a complex variable. Means that the real part of z tells you what distance you are horizontally, and the imaginary part of z tells you what distance you are vertically. And so the complex potential for uniform flow looks like this. And why do I say that? Because according to the Cauchy-Riemann equation that we had before, dw dz is just going to be u naught minus I v naught. And remember, we said that basically this component was going to equal to u, and this component was v. U is equal to u naught, and v is equal to v naught. I like to put the knots underneath those so you know that u naught and v naught are given constants. U naught and v naught is equal to constants. They basically determine what direction the uniform flow is in. But honestly, for a lot of your career, you can probably get along with v naught being 0, because you're just going to assume that flow is coming from the left, because you can always make your coordinate system associated with what your body's direction of your body. So any questions on this complex potential and z and how I got this? Yeah. This is not vorticity. Yeah, because these are all 2D flows.
Okay.
So these are 2D flows. So a couple things. 2D flows here. Here, if I say W of Z, this is W. U. Double U. Not vorticity. Because vorticity is some separate value. All right. This is the complex potential. We call this the complex potential. The complex potential has information on the stream on phi and psi in it. All right. Otherwise, any questions on how I took this derivative? It's linear with z. So when we take the derivative of z, you just this is a constant because u naught and v naught are given in the problem, and then basically you get this. And basically, when we have a complex potential, the derivative of it, dw dz, tells you all the information about the flow. In particular, it says that the real part is equal to the horizontal velocity, and the imaginary part is the vertical velocity. Okay. All right. So this is why, even this time's like, why would I want to do this like crazy notation? Well, it's because in complex analysis, they do a lot of things called mappings. And you can actually get flows that are actually really useful even though they don't look like each other. For example, and this is where actually math can actually get kind of useful. Because if you stayed in the real world and don't go to the complex world, you wouldn't be able to calculate these as easily. For example, a flow at a wall angle. So flow at a wall angle, we're going to call the complex potential W of z is a z to the n. Okay. So physically, what does that correspond to? That corresponds to wall angle is not the greatest notation, but it corresponds to you have like a wedge here, and theta is pi over little n, which is the same as the exponent. And then lines of size equal constant look like this. So basically, that tells you, what the flow looks like as it turns a corner. Okay. All right. And now this kind of might blow your mind, but this idea of flow at a wall angle will allow you to figure out things like the following special cases. 1. If you have n equals to 1/2, it's basically like flow around a plate. So if you got, so these would be the streamlines. This would be size equal constant. And then equal potential lines. I'm trying to draw this parallel to phi. So this is phi is equal to constant. Okay. So this is like flow around a plate. Let's just go down here. Flow, and you can have flow in a corner. For example, you have n equals to 2. If I have a 90-degree corner, it's going to look like just I had before, except it's going to go like this. Okay. And this is, so lines of symmetry. We also use a lot of lines of symmetry. For example, flow around a 90 degree, so in a 90-degree corner. So this is 90 degrees. This is also the same thing as modeling what's called stagnation point flow. Stagnation point flow is if I've got an infinite plate. I've got one line of symmetry that separates the left and right. And you can imagine the left and right are mirror images of each other. This dot here is the stagnation point. And so basically, people don't try to model both sides because they're identical, so they just model the right, for example, the right side, like I have here. Okay. So, and that's the case if basically W is AZ to the N, and you change your N to be N equals 2 or N equals 1/2. We're going to do sources and sinks next. You got to go. Yeah. Sources and sinks. The complex potential is m over 2 pi log of z. So, or m is the source strength. All right. So physically, what does that look like? It means if you're at the origin, you've got flow going out in all directions. Okay. You can show, so if W is log of Z, you can use some identities with complex. For example, if Z is equal to R e to the I theta, you can write this as phi is equal to log R, psi is equal to m over 2 pi theta. And that means UR is equal to m over 2 pi r, and U theta is equal to 0. And so in this case, for example, equal potential lines, basically, I think we might have talked about this before, but this is like, so this is a radial velocity decreases, goes as 1 over r, goes as 1 over r. That's associated with a conservation of mass, so that, you know, as you increase your radius, you have a higher perimeter, and so your velocity has to go down. So this would be, these are lines of constant phi. And this size equal constant.
This is a big deal in acoustics, the source and sink stuff.
A source in acoustics is like a source of sound or something, and a sink is what? Oh, but they have them in acoustics too. Maybe like a damping thing, like something that absorbs sound. Like that's why they have all those weird things on the. Yeah, that's why whatever this is. That's why we pay the big bucks for that piece of whatever sponge. And it's not just a big. So there's also a direct analogy with electricity and magnetism. Okay. So, for example, potential flow and electrostatics. Okay, we have a couple variables here. Let's talk about what they mean. Here, U is the same thing as electric field. M, which is they called it the strength of the source, but it kind of gives you an idea of the flow rate, because if you look at the units of M, it's basically velocity times radius, right? And in 2D, that's flow rate, velocity times perimeter. So M is the same thing as Q is charge. What is Q charge? Phi, and we have phi and electrical potential. I think that's voltage. Voltage and potential are the same thing, right? Okay. And this would be, I think this is charge. Okay. So there's this direct analogy. In fact, Gauss's law says that M is equal to 2 pi r times U of r. Gauss's law in E and M says basically Q is equal to basically E times some like epsilon or something like that. So these are analogous. All right. So flow of electrons is exactly like flow of molecules. When we flow electrons, you generate things like voltage and things like that. We don't get like a voltage in fluid mechanics. We can't use that for anything, but that's the idea, that you have potentials that are driving flows. Yeah.
What if I don't understand the comparison with the sources and the sinks. Like, how is it linked to?
Well, this analogy isn't just for a source and sink. It's true for all potential flows. But sources and sinks, basically it's imagine, okay, I've got the little dot here. That's like, in 2D, it would be imagine you take your, like if I wash my dishes, I wash my dishes, and I have a jet from my faucet hitting the plate, and then all the fluid's going out. So if you're like an ant on the plate, you're like, oh, I don't know what's going on, but all this fluid's going out. That's like a source. It means like your faucet, and the thinner your faucet is, the more that fluid's going out. And it just goes out in all directions. And the sink would be if I cut a hole in the plate and I've got fluid all leaving in the third dimension. But it's a source of fluid or a sink of fluid. Fluid, the fluid goes away at those points for sinks. Yeah. That's what a source and sink is. And it's associated with basically radial streamlines. So all the streamlines are just going out in some arbitrary angle theta. And it also has this idea that the velocity, as you go away from the source, you have decreasing velocity because of conservation of mass. Because you have a constant volume going in through here. A volume per time is the same thing as an area per time going in 2D, and that's equivalent to having an M. Your M is basically your volume per time. So maybe I'll just write that. M is volumetric flow rate. Yeah, that's exactly right. A sink is the same equation, except it's just M is negative. M equals negative for sinks. Because imagine it's the flow just changing direction. Okay, good questions. Wow. Okay. So there's a couple methods you can use to solve problems. You can use superposition. So we talked about that Laplace equation, the right-hand side is 0, superposition. So remember, you're selling del squared phi is equal to del squared psi is equal to 0. So you could have basically phi 1 plus phi 2 is equal to 0. That means del squared of phi 1 plus phi 2 is equal to 0 if and only if del squared phi 1 is 0 and del squared phi 2 is 0. So you can, and that's basically what people use. So superposition, so deduces W of z for multiple sources and sinks. So for example, for the homework, you have to add a uniform flow plus a doublet plus a vortex. The last irrotation flow I'll give you that's useful is the vortex. We talked about this in 2D streamlines, but we didn't talk about it in complex potentials. W of z is negative I gamma over 2 pi log z. And that corresponds to something that looks like this. Okay. Remember, my velocity is positive in the theta hat. That's why I drew in that direction. And basically, you have ur is equal to 0. U theta is equal to gamma over 2 pi r, associated with positive theta hat. And the vortex is kind of like the dipole. The dipole. I think they also call this the doublet. In my undergrad book, they called it the doublet. I don't know. I think a doublet is like the medieval armor you used to wear around your chest, but I don't know why I got pulled into this field. But here it's basically you got a source. You got like kind of like two vortices that are really, really close together. So you got this is log of z plus epsilon minus m over 2 pi log of z minus epsilon. And if it goes to a point dipole, as epsilon goes to 0. Because in that case, you got omega of z is m epsilon over pi z. And this, we call this m over z. Okay. So let's draw. So this is the irrotational. That's the irrotational vortex. What the doublet this looks like, it's if you have basically you got 2 points here by epsilon, negative epsilon. You kind of got a flow that's going to go between these two. You can imagine the same thing is going to happen now down here. And as you bring them really, really close together, they look towards each other. Okay, we're a little bit over. I think we're over time. But for example, the cylinder is a point dipole plus the uniform flow, and the circulation is 3 of them together. And I'll write that next time after the quiz, and you'll be able to proceed with that for the homework. So next week, I think we're going to go over the homework, and I might talk a little bit about low Reynolds number flow, because we kind of have we don't have enough lectures left to do another quiz, unfortunately. Fortunately for you, the bell's going to ring. So we'll probably talk about. I'll probably end the course talking about low Reynolds number flows. There's this we didn't really get to solve high Reynolds number stuff. I got some low Reynolds number stuff. Yeah. They're kind of like the same. Parallel and tangent is the same thing. Parallel is kind of like